about the difficulty level of the course. Is it difficult for you guys? Easy? How is the pace? Okay, just write your feelings in the chat. And we can have a look at them. Okay, so if there aren't any comments, let's start today's lecture. So we'll start with a short review of what we did yesterday. So yesterday we saw that the linear regression setup is general. It doesn't have to have polynomial basis. It can have any basis. So in general, we can write y is equal to aw plus a, where a can be any basis. And so on. And the setup would work. The optimal solution W star would be A transpose A inverse A transpose Y. Okay. And we saw that different bases might have different advantages in different cases. Then we saw some regularization techniques. In certain cases, you might run into the problem of overfitting, and to avoid these issues, what you can do is you can add a regularizing term in the objective. And in that case, the optimal solution in the case of L2 norm regularization was and then you don't, the overfitting in these cases is not very severe. The design choices that you have to choose a right value of lambda. You don't want to have too small a value of lambda, in which case you would have overfitting. You don't want to have too large a value of lambda, in which case all your weights would be close to zero. Okay. So with this, let's look at an outline for today's lecture. So if you remember our original day one lecture slide, we had artificial intelligence, which is a broad umbrella for all algorithms which can sense, learn, reason, and act. Under this, we had machine learning algorithms, which were data-driven algorithms, where the learning happens from data. Under machine learning, we had unsupervised learning and supervised learning. The difference between unsupervised and supervised learning is that in unsupervised learning, you don't have labels. In supervised learning, you have the labels. And under the supervised learning, we had two categories, which was regression and classification. So we have done this. Today, we would look into classification. Okay. And then we would see some associated concepts with classification problem and how do we set them up. Okay. So let's look at what a classification problem is. So in classification problem, you have some data, X, and some output Y. I'll assume X to be one-dimensional. Yeah. So for some values of X, let's say 0, 1, 2, 3, the output would be, the class label would be 0. And for certain other values of X, the class label would be 1. That's a classification problem. Okay. So this, in the examples that we saw, let's say that we are interested in a classification problem where we are trying to find cat in an image. In that case, 1 would mean that there is a cat in an image. It belongs to class cat. And 0 would mean that it does not belong to class cat. Why do we convert these concepts like cat, dog, elephant, or let's say if you are any other concept, why do we convert it into numbers? Why do we give them a number 0, 1, something like that? Because we want to do mathematical operations on them. We want to do the optimization process on them. It's difficult to, if the output label was, let's say, cat or dog, and your network, you had some network which can just tell you whether it's cat or dog, does not encode the mud number, then how do you do these minimization steps? How do you construct loss for a name cat and a name dog? You cannot. So we have to convert these concepts into numbers, into class labels. Okay. So now, okay. So we would have, for classification, you would have a data x. You would have a hypothesis function h of x, where h of x is not continuous anymore. H of s is in a set. In our case, let's look at a binary classification problem. It just gives you an answer 0 and 1. And then, of course, the same thing, you would have to have a loss function, a cost function, which depends on certain weight, and you want to optimize these weights. That would be the setup for classification problem. Okay, so let's see how this is different from the regression problem. So in regression problem, you had some data and you want to fix a line to it. So this is your h of x. Yeah, it's a continuous function. In classification problem, this is your decision boundary. So anything above it is labeled a class 1 and anything below it is labeled a class 0. Okay, similarly, this is your decision boundary and this is your decision boundary. Don't worry too much about how we do it. We will go through the setup of doing it. But for now, let's just look at the abstract concept that this line, which we are trying to learn in space, this is a decision boundary, which divides your data into two parts, in two classes, in the case of binary classification. Okay. So let's start with a recap of linear regression. So what we had in linear regression was something like this. You have data, xi's and yi's. You have endpoints from I equal to 1 to n. In our notation, we generally write it 0. And then x is in n dimension. We call this m dimension, where m is the number of bases. And yi is your label, which is a real number in our case. Okay. So what we did was we constructed a mean square error loss for it. And then we try to find the optimal parameters, and we show that we can find it in closed form. Okay, this was our solution, h of x. The blue points was our data. Okay, in logistic regression, we want something like this. We want a linear decision boundary. So this would be equivalent to your bases or your you can call them basis functions, or your different variables. And we want this line, a linear decision boundary between the two classes. So anything above this line would be class 1, and anything below this line would be class 2. Okay? This is how the data looks. So the main difference between the data is that the two data is that y now is in a set 0 and 1. It's not a continuous variable. Okay. In the previous case, so this is for classification. For regression, we had y in a set of real numbers. Y was a real number. It could have any value. Now y is not a real number. Y is just from a set, it's 0 and 1. So let's see what type of problems come with it and how do we set up solutions for this. So the thing is, why is this important? Where do these classification problems come in real life? If you look at the applications of machine learning which have created most impact in terms of financial gain, it's these classification applications. For example, regular or fraudulent transaction. Let's say you're working for a bank, and your bank has produced an app, and on that app you get, let's say, 100,000 transactions per day, but you want to have a mechanism whereby you can see whether a certain transaction is fraudulent and then flag it and ask them for additional information. How would you do it? That's a classification problem, right? Based on some data about the type of transactions that being made, the type of app or the type of device from which the transaction is happening, you would either say that this transaction is fraudulent or you would say it's a regular transaction. Similarly, another important one is the spam or non-spam email. So if you guys have used email for a few years, you would have seen that these spam filters are becoming better and better. They're becoming very efficient in telling which email is genuine and which email is a spam. Well, this is also a classification problem. So the email engine would look at the data in the email or the content in the email, the type of email addresses from which the email is coming, and it would try to figure out whether this is a genuine email or whether it's a malicious email. Some examples from medical field, benign and malignant tumor. So let's say you have specifications for a tumor, you know its size, you know its shape, you know its opacity on an X-ray or something like that, and you want to classify it whether it's a real or malignant tumor, you would use a classification type of algorithm. And finally, from finance market, rising and falling stocks. Well, this is not exactly a classification problem, it's a regression problem if you want to calculate the exact value of the stock, but you might not be interested in the exact value, you might just be interested in finding whether you are going to earn money or you're going to lose money. So then it becomes a classification problem. It's either +1 if you are making money, or it's 0 if you are not making money. So the problem setup changes slightly. You have 0 to n points. Xi is in Rm, where m is the space in which you're working. It's the number of bases. And yi is is in a set 0 and 1. Does everyone understand the setup of classification? Like, how is classification different from regression? What is the setup of classification? Everyone is clear on that? Okay, I want to see some more yeses so that I know that most of us. Let's see what somebody's asking. Kevin, for your question, I did not understand it. Will our courseware be posted? I don't understand the question. So please put it again in the comment and I'll have a look at it. Okay, so let's start. Let's see what we did let's try to build up on our previous knowledge and try to do something with that. Okay? So what have we done up till now? Up till now, we have a setup where we can, if you have y, you can write it in terms of a hypothesis function, w0 plus w1x plus w2 2x squared plus w and x power n. And let me just not write it h, x, y, let me write it as hypothesis function h. So this is h of x. Okay, this is regression, linear regression. It is. What I say is that let me try to use this in my classification problem as well. Okay, let's say, what is the setup for classification problem? The setup for classification problem is this: you have data x and you have output y. Okay, so what I'm trying to say is that let me write my hypothesis function as this composed with something else. So let me write my setup first and then try to see what you guys think about it. So I would say that my logistic regression is something like this. So first I call this function, rather than h of x, I call it a of x. Okay, or in fact, better term is z of x. And I say that z of x is w0 plus w1 of x plus w2 of x squared up till wm of x power n. This is going to be z. I'm setting up, I mean, whether you will put the slides. Yes, I'll put the slides on the website. I didn't put it for yesterday's lecture, but I'll do it today during the break. Okay, so this is Z. Okay, now let's say that we have a function, some function. I'm not going to say which function is it. Let me call this function sigma. So I take sigma of Z, and sigma of Z is such that um, its output is, let's say, in 0 and 1. Okay, so what I say is that rather than coming up with something new, let's use what we have learned so far. So we take the linear regression model, we use the linear regression model, and we take the output of the linear regression model into a function, sigma, which gives us output 0 and 1. So now it's a classification problem. So the pipeline would look something like this. For x, you would pass it through this function z, then you would pass it through the function sigma, and the output would be your hypothesis function, because now it's 0 and 1. Does it make sense? Does everyone understand my pipeline? Okay, perfect. Okay, so now let's see. Let's try to see how we can set up this pipeline. Of course, in front of this, there is again, then you would have a cost function where true labels would be coming out and you would be optimizing the weights W. And the weights are in this part. So we have designed it that sigma does not have any weights. But let's look at it in a little bit of detail in the coming slides. Okay. A side note that although we call it logistic regression, it's a classification algorithm. Okay. It's a classification. You use it for classification. So again, this is a linear model in disguise because we are using, under the hood, we are using linear regression. So this is exactly like our setup. This is, let me call this W transpose X. So this is exactly like our setup. This is W0 plus W1X plus W2X plus WN. XN. Okay, and these are W's. Okay, and this we call it Z of X rather than Y hat. Okay, so let me ask you some questions now at this point. Okay, so question number one. Let's assume that we have this setup where you have X and Y. X is certain data, Y is its class label. Okay, you pass it through a linear function similar to a linear regression type of setup. Then you pass it through a function which gives class label, which output for which is 0 and 1. Then you set up a cost function. Okay? Then you pass it through a cost function, which takes in the real label, and this your hypothesis function h of x, and you want to run some optimization to find the optimal weight. Now, my question for you guys is that let's say that my hypothesis function is such that you get 0 and 1. So hypothesis function, the output of hypothesis function is 0 and 1. What is the possible problem that you foresee? If, for example, we were able to create a hypothesis function, the output for which are discrete, 0 and 1, what is the issue that you guys foresee in order for us to find the optimal weights for this learning algorithm? Is there any problem with this? If, for example, we are able to get discrete labels from our hypothesis function, what issues do we foresee? Can we find a solution for this, this cost function? If, for example, I write J, which is, let's say I use linear least squares, the same square norm error. So I have y minus h of x whole square for all points. can I find the best value of weights? Can I find W star if h of x is discrete? So how did we find the optimal of our cost function? What did we do? So once we get J, what did we do to find the best value of weights? Come on, guys. How do we find the minimum of a function? Yes, we take the derivative and set it equal to 0. Okay. Can we take the derivative of a function which has discrete values? No. So then it means that we are stuck, right? Because we have a function h of x which has discrete values. And like you guys said, we cannot have the derivatives for a function which has discrete values are not defined. It's not defined, it's undefined. Okay, then what should we do? It seems like we have a problem. So we want h of x, the output, to be class labels. But if the output is indeed class label, then we cannot find the derivative. And we cannot find the best values of our weights to give that output. What should we do? What's the solution for that? Any ideas? So remember, let me just write the definition of derivative. So the derivative of a function at x is f of x plus delta x minus f of x divided by delta x, limit delta x approaches 0. Okay? But, for example, if a function is not continuous, if it is discrete like this, then you would see that the derivatives are undefined everywhere. Or at least at these points, the derivatives are not defined. So what can we do? The solution is just to reformulate the way we think about the problem. So rather than saying that our hypothesis function gave us the class label, we said that our hypothesis function would give us the probability of the sample belonging to a certain class. Okay, so let me rewrite the setup. So our data was 0, 1, 2, and the output was 0, 0, 0, and then 2, 3, 4, 5, and 1, 1. So I would say that my hypothesis function is y hat, or let's call it y, equal to 1 given x. So what is the probability for a sample to belong to class 1? So for this, for class 0, if you have a well-trained network, if you have learned something nice, these values would be small, right? Maybe 0.01 and 0.2, and this should be large, 0.9, 0.8, 0.7. So rather than displaying the output label of your data, you try to find the probability that your sample belongs to a certain class. And probability is a continuous variable between 0 and 1, right? So things should be fine. Is everyone with me? Does everyone understand what's the motivation of using probabilities of belonging to a certain class rather than the class label in our setup?
Yes.
Okay, perfect. Can I see some more yeses in the chat so that I know that? Perfect. Okay. So thank you very much. Okay. So now let's come back to our setup. So this was our setup. Said that we have an input X. We have a linear layer. Then we have a sigma function. And then we have cost function and so on. Okay. So if, for example, my X is a real number, and we have certain bases here, all these bases, of course, would be real number. The output of Z, let's call it Z of X. This would also be a real number, right? So Z of X can be any real number. It's a scalar because our output is just a single variable. So we have an input here, which can be any real number. And at the output, sigma of z, we want it to belong to 0 and 1. Why do we want it in this interval? Because it's a probability, right? It has to represent the probability of the output label being 1 given a data sample. And probability is bounded between 0 and 1, 0 and 1 inclusive. Okay. So do we know some functions which can do that for us? Do we know a sigma, a function, which takes in a real number and outputs a number between 0 and 1? ReLU probably not, because ReLU is bounded between 0 and positive infinity. Sigmoid, yes. So sigmoid can do it for us. Okay, so let's write what a sigmoid is. What's the definition of a sigmoid function? So sigmoid function is defined like this. It's 1 divided by 1 plus exponent minus c. Okay, and we claim that this is bounded between 0 and 1. So let's try to plot it and let's see what happens. So exponent is a monotonic function. Okay, so exponent minus z would be again monotonically decreasing function. So if we look at the values at the extremes, at the limits, we can say that the function would be bounded because this quantity, as you increase the value of z, this is a decreasing quantity, always decreasing quantity. So let's look at the value of sigma of z at the edges as z approaches negative infinity and z approaches positive infinity. Okay. So let's say that this is z, and I'm trying to plot sigma of z. So let's see, sigma of z, limit z approaches negative infinity. This will be 1 divided by 1 plus exponent minus z, limit z approaches negative infinity. So what happened to exponent of minus z when z approaches negative infinity? So as z approaches negative infinity, this quantity inside would approach positive infinity, and exponent of positive infinity would approach infinity. Everyone understands this? Okay. Okay, if this quantity in the denominator approaches positive infinity, 1 divided by a quantity which approaches positive infinity would approach 0, right? So this would approach 0. So at negative infinity, the sigmoid values are very small. At 0, exponent of 0 is 1. So you have 1 divided, let me just write it here. Sigma of 0 is equal to 1 divided by 1 plus 1, which is equal to 1 by 2. Because at 0, exponent minus z is 1. So you get a value 0.5. So this is how, roughly, I'm sketching it roughly. This is how the sigmoid looks from negative infinity to 0. Now let's look at the value of sigmoid at positive infinity as z approaches positive infinity. So limit z approaches positive infinity, 1 divided by 1 plus exponent minus c. So as z approaches positive infinity, minus z would approach negative infinity, and exponent of minus z as z approaches negative infinity is 0, right? I want to see some yeses, okay. So as this approaches 0, 1 divided by 1 would be equal to 1. So something like this. So it does indeed, it asymptotically reaches 1 and it's asymptotically reaches 0. It approaches 1 when z approaches positive infinity. It approaches 0 when z approaches negative infinity. So it is indeed bounded between 0 and 1. So the first challenge that we had, we have solved it. We have come up with a setup which would give us a number, which is the probability of the class label being 1 for a data point. So now we are half set. Let's redraw our pipeline. So our pipeline is this. You would have a linear layer. Linear layer, when I say linear layer, it's just linear regression. Okay. Then you would have an activation. These non-linearities in neural networks are called activation. So when I say activation, I mean the sigmoid function. Okay. After that, this would give you your hypothesis function. You have a cost function. The input is y, and it would give you some value for loss, okay, or your cost. So the next thing is setting up a cost function. So we already have a cost function which we have used in linear regression, which is the square norm. You take the square of the difference between y and y hat, and you add it up for all data points. So the cost function in the case of linear regression was I equal to 1 to n, y minus yi minus h of xi whole square, right? In practice, we see that this loss function is not a good loss function for logistic regression or for classification problems. So this is not good for classification problems. So what do? We try to construct another loss function which is more tailored to classification type of application. Yeah. And let me just write the sketch for that loss function. So what do we want this loss function to be? So basically, we want our cost function, which takes in y and h of x. And we want it to compare y and h of x. Okay. H of x, I'm assuming, is a class label. And it should be 1 if they are not similar. And it should be 0 if they are similar. So for example, if the output class is 1 and your network says that your class label is 1, the loss should be 0 because both the labels are same. But if the true label is 1 and your network says the label is 0, you should get a high loss, right? But we have reformulated our problem slightly. We're saying that h of x is actually the probability that y is equal to 1 given x, right? So for these type of setups, we use metrics on probability. So we have certain metrics on probability which checks the difference between two probability distribution. It's slightly advanced at this level. What I can do is directly give you the loss function and then look at its motivation. Okay, so let me just write this here. Y hat is h of x. So whenever I write y hat, I mean h of x. So the loss function j is defined as negative y log of y hat minus 1 minus y log of 1 minus y hat. Okay, and that's called, this loss function is called binary cross entropy loss. Okay, let's see why this is a good loss function. Let's try to plot it and let's see what happens. Okay, so what does this loss function depend on? What is the independent variable in the expression of j? So there are two variables, y and y hat. Which one is independent and which one is fixed for a given data? For a given data, y is fixed, right? Because y is your label. So you would be given this, x and y. So y is fixed, y is not changing. So what's the independent variable? Y hat, right? So let's try to plot this loss function against y hat. Okay, thank you. And what are the possible values of y hat? Which interval do I need to plot it on? Just 0 and 1, exactly. So we need to plot it between 0 and 1. Okay, so what are the possible values for y? It's a binary classification problem. So what are possible values for y? 0 and 1, exactly. So let's first look at the case when y is equal to 1. So I'm just going to take a different color. First, I look at the case when y is equal to 1. Okay, when y is equal to 1, this term goes to 0, right? Because it has this 1 minus 1 here. So let's try to plot this part. So on the side, let me just do this. Let me plot y hat and log of y hat. So what is, and I have to plot it between 0 and 1. So what is log of y hat when y hat approaches 0? What is log of very small positive numbers? So I'm asking you this. Log of y hat, limit y hat approaches 0. What do we get here? This approaches infinity, right? Exactly. And what is the log of 1? Log of 1 is 0. So basically, this is the function of your log. This is how log looks in this interval. Okay. And what are we plotting here? What do we have here? We have a minus sign, right? So we will flip this. So basically, the loss function would look like this. Everyone understands this? If y is equal to 1, my loss function is this. This is 2. Everyone is with me on the same page? Everybody understands how the loss function looks? Excellent, excellent, great. So now let's look at what this means. So if y is equal to 1, what does y hat represent? Y hat represents probability of y equal to 1 given x, right? If the actual label is 1, we want y hat to be 1 as well. We want y hat to be high. Because if the true label is 1, we want our network to say that, yes, the probability of the label being 1 is high, right? So when probability is actually 1 and your network says that it is 1, you have very small loss, which is nice. But when the actual label is 1, but your network thinks that the label is actually not 1, you get very high loss. So this is exactly what we want in a loss, right? So everyone is clear why this is a good loss function for the part, at least for half of the part when y is equal to 1. Excellent. Let's look at the second part. Second part is y equal to 0. So when y equal to 0, this part goes to 0, right? And we have to just look at this part, log of 1 minus y hat. Okay, so let me plot this here. First, let's just plot log of 1 minus y hat. Okay, so when y hat approaches 1, 1 minus y hat approaches 0, and you would see that this would be like this. Y hat approaches 0, 1 minus y hat approaches 1, and you get 0. Everyone understands how I plot log of 1 minus y hat? Okay, perfect. Now let's plot negative minus negative log of 1 minus y hat, and this would look like this. So let's try to interpret what this means. If y hat is 0, you want the probability of y equal to 1 given x to be small. And that's why at this part, your loss is small. If the true label is 0 and your network believes that probability of the label being 1 is small, it means that you are correct, right? If probability of being 1 is small, then it means that probability of being 0 is high, right? So that's why you have a small cost here and a large cost here. So this means that the loss function is indeed a good loss function. It is trying to do what we want it to do. When the label is 1 and your network believes that the label is 1, your loss is small. When the network is 1, when the label is 1 and your network believes that the label is not 1, your loss is high, and vice versa for label 0. So this seems like a good loss function. Okay, let's quickly see some formalized version of this. So sigma is defined like this. It's widely used in classification. These are exactly the things that we did mathematically. Just want it to be on the slide so that you can review it. The next thing was the cost function, and we said that we would use a cost function like this. We found the shape of the cost function and we plot it. Now let's come to the main crux of the problem, which is finding the right weights. So basically, the entire pipeline looks like this. So you have an X, you do a linear regression, you pass it through a linear regression model, you pass it through a sigmoid, and you give it to a cost function, which takes in this y hat and y, and gives you a number, some loss, some value of loss. Okay. How do we find the right value of weights? Remember, z of x is w0 plus w1x plus w2x squared, and so on. How do we find these right weights? Okay. We use the same setup that we did for linear regression, and we try to find the derivative or gradient with respect to of the loss function with respect to the weights, and set it equal to 0. Okay? So basically what we need to do is we need to take this, find its gradient with respect to w, and set it equal to 0. Okay? So let's do it. Let's do it for a small toy problem. Okay. So I would take a small problem in 2D. This, by the way, is exercise 5.4 that you guys have to do today. So what I do is I have a two-dimensional X. So X is basically X1 and X2. I have a 2D point and I have a label for it. So let's say that this might be something like 0, 0, and maybe here it's the label is 1, and then 0, 1, the label is 1, 1, 1, the label is 1. And then for certain large points, maybe 2, 2, the label is 0, 2, 3, the label is 0, 3, 2, the label is 0. So you have 2D data. So 1 and X2. Remember that you can think of multidimensional vectors as just each individual component of it as a base. So my z of x would be w0 plus w1 of x1 plus w2 of x2. Okay, that's the linear regression part. Then I pass it through a sigmoid, and that's just simply 1 divided by 1 plus exponent minus c. Okay, and then I pass it through the cost function. J of this is also y hat. So j of y and y hat, which is negative y log of y hat minus 1 minus y log of 1 minus y hat. And now what I need to do is find the, let me just do partial derivatives because it might be a little easy to understand. So I have to find partial derivative of j with respect to w0. I have to find partial derivative of j with respect to w1. And I have to find the partial derivative of j with respect to w2. Then I have to set them equal to 0, solve the system of equations to get the best value for my weights. Everyone is clear about the setup, what we have to do?
Yes.
Perfect. Perfect. So now let's try to do it. Let's try to find the partial derivative of j with respect to w0. Okay, I'm going to write an expression and then we're going to discuss it whether you guys are familiar with it or not. Can I write it like this? Can I say that partial derivative of j with respect to w0 is partial derivative of j with respect to y hat, or in fact it's just a function of that, so d by dy hat times dy hat times dz times partial derivative of c with respect to w0. Can I do that? And what is this called from calculus? Okay, I can do that. This is a correct expression, but what is it called? This is chain rule. Okay, so chain rule is just a quick introduction of chain rule. So for example, if you have something like this, let's call it, u, v, w, x. Okay, so let's call f of u equal to v. Okay, f1, let's call it 1. Let's say f2 of v is equal to w. And let's say f3 of w is equal to y. Okay, and let's say I'm interested in finding the derivative of y with respect to u. Okay, what I can do is I can break it down into parts. I can find the derivative of y with respect to w first. So I'll find the derivative of y with respect to w. Then I'll take the derivative of w with respect to v, derivative of w with respect to v. Then I'll take the derivative of v with respect to u, derivative of v with respect to u, and that's exactly equivalent to derivative of y with respect to u. That's called chain rule. Everyone is on the same page as with us?
Yes.
Okay, I need to see some more yeses so that we know that we are indeed following chain rule. Perfect, that's all the calculus we need. Chain rule is all the calculus that we need in machine learning and artificial intelligence. We will be good if we know it. So let's come back to our slide and let's get a clean slide and try to derive these expressions. So of course, we have them in closed form, but I want to derive it so that we see that it's not, there is no magic. It's quite simple expressions and we can actually do it. So let me write it here. So Z is W0 plus W1 x1 plus W2 x2. And then Y hat is 1 divided by 1 plus exponent of minus C. And then J of y hat is negative y log of y hat minus 1 minus y log of 1 minus y hat. So let's first find the derivative of j with respect to y hat. Okay. So of course y is constant with respect to y hat, so you have minus y. The derivative of log of y hat with respect to y hat is, what is the derivative of log of x with respect to x? It's 1 by x. So this is y hat and then minus 1 minus y. The derivative of log of 1 minus y hat with respect to y hat is 1 minus y hat times minus 1. Again, I've applied chain rule. So you take the derivative of log of 1 minus y hat with respect to 1 minus y hat, which is exactly equal to 1 divided by 1 minus y hat, and then the derivative of 1 minus y hat with respect to y hat, which is minus 1. Okay? So this becomes minus y divided by y hat plus 1 minus y divided by 1 minus y hat. And I can take the LCM, the denominator, this becomes 1 minus y, 1 minus y hat plus y hat, 1 minus y hat, sorry, 1 minus y. And this becomes minus y plus y hat plus y hat minus y hat divided by y hat 1 minus y hat, and these two cancels out, y hat minus y divided by y hat 1 minus y hat. Okay, is this clear to everyone?
Yes.
This simple calculation. Okay, let's store this, we are going to need it. Let's calculate the second thing. What is the second thing? It's the derivative of y hat with respect to z. So let's calculate that. So derivative of y hat with respect to z, and we know that y hat is 1 divided by 1 plus exponent minus z. So basically, can I write it like this? dy dz of 1 plus exponent minus z times minus 1, power minus 1. I just brought the denominator to the top, give it a power minus 1. Again, I will apply chain rule. So first I apply the power rule of derivatives on this term. This becomes minus 1, 1 plus exponent minus z times minus 2, power minus 2, I'm sorry, it's then I take the derivative of the inside term. So exponent minus z's derivative is exponent minus z times minus 1. Is it clear to everyone? Does everyone agree with the derivative?
Yes.
So these two cancel out, and I have exponent minus z divided by 1 plus exponent minus z whole square. Can I do something like plus 1 and minus 1 in the numerator? Of course I can. You can add and subtract the same quantity. So this becomes 1 plus exponent minus z divided by 1 plus exponent minus z whole square minus 1 divided by 1 plus exponent minus z whole square. Okay, and this cancels out with this. So this becomes 1 plus 1 divided by 1 plus exponent minus z. And what is this? This is exactly y hat, right? So I can write it as y hat minus, what is this? This is y hat, this quantity. This is just y hat square, right? So 1 divided by 1 plus exponent minus z whole square is just y hat square. Is everyone with me?
Yes.
Okay. So this becomes y hat 1 minus y hat. So this is the second term. And lastly, we need z was w0 plus w1x plus w2x2. We need the derivative of z with respect to w0, which is 1, the derivative of z with respect to w1, which is x1, and the derivative of z with respect to w2, which is x2. So now we have everything we need. we can find partial derivative of j with respect to w0, which would be equal to derivative of j with respect to y hat times derivatives of y hat with respect to z times the partial derivative of z with respect to w0. We can just put in the values. J with respect to y hat is y hat minus y hat divided by 1 minus y hat. So let me just write it. So y hat minus y divided by y hat 1 minus y hat. Derivative of y hat with respect to z is y hat 1 minus y hat. This becomes y hat 1 minus y hat. And the derivative of z with respect to w naught is 1. So these two cancel out. And this just simply becomes y hat minus y. Okay. Similarly, the derivative of j with respect to w1 is dj derivative of j with respect to y hat, derivative of y hat with respect to z, partial derivative of z with respect to w1. This is y hat minus y divided by y hat 1 minus y hat times y hat 1 minus y hat. Again, these two cancels out times what is the partial derivative of z with respect to w1? It's x1. So this becomes y hat minus y times x1. And you can do it partial derivative of j with respect to w2. This would be y hat minus y times x2. So now we have the gradients for the derivatives of cost function of logistic regression with respect to the weights. So let's put them in a vector. So this is j with respect to w. This is y hat minus y hat minus y times x1, y hat minus y times x2, and let's set it equal to 0 and try to solve it and try to find the right values of weights. Do you think it's straightforward? Can we find the solution directly? So remember, y hat is 1 divided by 1 plus exponent w0 plus w1x plus w2x. So we have three nonlinear equations, and we have to find the solution of a set of three nonlinear equations. Do we have a closed form solution for it, like we did in the case of linear regression? Well, the answer is no. We don't have a closed form solution for this system of nonlinear equations. Then how do we solve it? How do we solve this system of nonlinear equation? Well, there are some ways. One of these is like iterative method, like Newton method. So you can linearize the system of nonlinear equation, solve it, and then do it iteratively until you find a solution. But that's expensive. In general, let's say if you have a function f of x, right, which is a highly nonlinear function, and you want to find a minima for this function, what you can do is you can use something of some sort of iterative approaches to find its minima. So let's say that f of x is highly nonlinear. And the task is to find its minima, to find a local minima. Let's not call it a minima, a local minima. So x is, f of x is a nonlinear function, something like this, okay? And we want to find a local minima. What we can do is we can use a family of techniques which are called gradient descent methods. We will have some more discussion of gradient descent method in the coming lecture, but today I'll just give the summary for a quick introduction of what people do. So what you do is you just initialize some value of x, let's say x naught. So you start with x naught, and then you say that on the function, go in the direction in which the value of the functions are decreased. So you have two options, right? At this point, you have two options. You can either go left or you can go right. In which direction does the value of function decrease? In the orange direction or green direction? Which direction is the function decreasing in? So orange direction, yes. So you take a step in the orange direction. You say that, okay, the next point I will come here, maybe here. Okay. So now again the same question: is the function decreasing in orange direction or is it decreasing in green direction? It's still decreasing in orange direction. So you will take a few more steps. Maybe you will come here and then here and so on. Eventually you will reach a local minimum. These are called gradient descent method. So basically the goal is at each time you just go in the direction in which the function is decreasing. Okay. In fact, the function is decreasing the most. So these are called gradient descent methods. Don't worry too much about it. We will have a detailed discussion of this method today, but let me just give a quick overview of gradient descent method. So what is the goal? The goal is to find a local minima for f of x. The algorithm is this. So initialize x to x naught. Okay. Then do something like this while the derivative of x is not equal to 0. Do this. What do you do? You calculate the derivative, find the derivative of f with respect to x, and update x as x minus the prime of x. So what is this doing? What does derivative represent, or what does gradient represent? Gradient represents the direction of maximum increase of the function. Okay. If I give you a gradient direction of a function, this gradient direction would represent the direction in which the function is increasing by maximum. Okay. But we want to decrease, we want to go in a direction in which the function is decreasing the most. So that would be negative gradient direction. Okay. So you stand at a point x and you take a step in the negative gradient direction, a direction in which the value of the function is decreasing the most, and then you keep on repeating it until you reach a point this, where the derivative is equal to 0. Until this condition is satisfied, you keep on doing it. When the derivative is 0, it means that you are indeed at a local minimum. I think it's probably better to show it in the figure. Yes. So we do something like this. You start with some random initialization. You take a step in the direction in which the function is decreasing, and you repeat it. You repeat it until you reach a minimum. And this direction of decrease of the function, is the direction of negative gradient. Because positive gradient is the direction of maximum increase, negative gradient would be direction of maximum decrease. So you take steps in the negative direction until you reach a minimum. Does it make sense to everyone why we go in the negative gradient direction?
Yes.
Okay, perfect. So now let's try to set up the problem for our coding exercise today, which is 5.4. So let me come to the last slide and set in the slide. So what is our exercise today? So you are given certain data into the training data, and you have to find a classifier you have to train a logistic regression classifier which can classify it. Okay, so what you need to do is you need to do this gradient descent operation on the cost function. So the first thing that you need to do is you need to, of course, find z. Z would be W0 plus W1 x1 plus W2 x2, because these are 2D points, so you have x1 and x2. Okay, two components of your data. Then you pass it through your sigmoid, so you get sigmoid of z. Then you pass it through your cost function, your loss function, j of y and y hat. This is called a forward pass. It's a neural networks term, but let's call it forward pass. After that, you will calculate the gradient of your cost function. So you will calculate the gradient of your cost function, which would be y hat minus y times y hat minus y times x1, y hat minus y times x2. Once you have this, you would update, you would, of course, start with initialization of w. So you would have initialize w0, w1, and w2. And then you would use this gradient to update it. You would say that w at iteration I plus 1 would be wi minus some learning rate. Keep it small, something like 0.001, or maybe smaller than that. Times the gradient of j with respect to w. So you calculate this thing, then you use it to update your weight. And you repeat it until you reach a minimum. Everyone follows this? So please ask questions, because the next 1 hour you guys have to try it. So it's better to understand it before you try it. So this is exercise 5.4 in the handbook. Is everyone clear about what you guys have to do? If not, please ask questions. I'll be more than happy to answer. Okay. Can I see some yeses in the chat that everyone is clear, so that I can lead you guys to it? Okay. Excellent. Excellent. Okay. So I will leave you guys to it. Give it a try. Give a try to question number 5.4. And we will meet. I will restart the lecture at 11:30 and we will solve it together. But I want you guys to give it a try first. I will be available in the chat till 11 for questions, and then from 11 to 11:30 we will have a 30 minutes break, and we will resume at 11:30 to solve this logistic regression problem. Okay, everyone's good? Perfect. Good luck, and I'm available in the chat if there are any questions for anyone. Okay, so what is the motivation of gradient descent methods? So let's first look at something. So let's say if I ask you, you have this, I give you an equation, highly nonlinear equation, let's say something like x exponent x times maybe sine of x, okay? And I ask you to find me some points at which the derivative of this function is equal to 0. Okay, how would we do it? How do we do it? Okay, so there are a set of methods, iterative methods, like Newton methods, which solve them iteratively. Okay, and how do they do it? So basically, let's say this is your function. Okay, Just to pass through this. So what does Newton method do? It would, this, let's say this is the derivative of this. Okay. This is the function f prime of x. Let's call it g of x for clarity. And you want to find where g of x is equal to 0. So what you do is you linearize the function. You say that, okay, at this point, my function is this linear approximation of g. And you find where this is 0. It's 0 here. So you say that this is my initialization for x. It's called an x0. After the first iteration, this is your x1. You come at this point. You again approximate your g with this linear approximation. You come here. This is your x2. You come here. You again approximate your g with the linear approximation. This is your x3. And you repeat this process until you maybe reach here, which is x4, which is your true solution. So one way to find the points where gradient is equal to 0 is to use these iterative techniques. Okay, these are called Newton method. Okay. There is a better technique to find a global minima, which is called gradient descent methods. So let me tell you what gradient descent method is. So it's a gradient descent method. So I'll put here, one technique is this, that you set f of x equal to 0 and then solve this system of equation. Okay. If the equations are non-linear, for non-linear equations, you would use something like Newton method. Iteratively find the solution. What you can do is you can do something better. So what is a minima? A minima is a point where a local minima where the value is locally the smallest. Okay. So what we say is that let's do this. Let's initialize x to x naught. Okay. While the derivative of f, in fact, because I'm in multidimensional, I'll call gradient, while the norm of gradient is not equal to 0. Do this. Step 1, find the gradient. Okay. Once you have the gradient, what do we know? What is the gradient direction? Gradient direction is the direction in which the function is increasing the most. I'm sorry. Gradient direction is the direction in which the function is increasing the most. And what do we want to do? We want to decrease our function. We want to go to an x which would decrease the value of our function. So to do this, we would say that x of I plus 1 would be x of I minus learning rate. This is a small number. I'll explain what is the purpose of this, but for now, let's assume that just pick a small number. And we take a step in the negative gradient direction. Notice that's negative sign. So basically, essentially what this would do is, let's say if this was your function, and this was x of 0, you will take a step in the direction in which the function is decreasing. You will come here. This would be x1. Then you will take another step here. This would be x2. The superscript represents time, the number of iteration. So in the first iteration, you are here. The second iteration, you are here. The third iteration, you are here. And eventually, you would reach a local minima because you're always going in the direction in which the function is decreasing. So think of it like you are in a dark room. Okay, you are in a dark room. You cannot see anything, but you are asked to go to the lowest point of this room. So what you can do is you just close your eyes and you, with your foot, you see in which direction is the room going down. So think of it as a stairs. So you just see in which direction is the stair downward, and you take a step in that direction. Then you come to a new point. You again look, okay, which direction should I go in order to move down? And you take a small step in that direction. And you repeat it until you reach the very low point or a low point of the room. Does it make sense? Is it clear? If it's not, please ask. It's fine. It's not. I should come up with a very good explanation so that everyone understands. The best thing that I do is when I'm like when I'm presenting it in a class is that I just show it on the stairs. Like I just stand on the stair, I close my eyes, and I say, okay, let's do gradient descent. So what do? Is I look at one direction, and this is stairs are going up. I look in the other direction, steps is going down. So I take a step in the direction in which the steps are going down, and the going down is the negative gradient direction. Then at the new point, I look again. I see which direction is step going up, which direction is step going down, and I take the step in the direction in which the step is going down. The stairs are going down, and you repeat it. So you would be going down one step each time until you reach the bottom point. What is the symbol after the minus sign? So this is called learning rate. This is called learning rate. This is a constant. So you just set this equal to 0.001. So this is a constant. Okay. So when I write this, you can just like in your calculation, you would just set it equal to 0.001 and don't change it. Just put it this. And why is this? Why do we need this learning rate? So just one, again, this is a topic for tomorrow's lecture, but I'll just give some explanation as to why we want to have this learning rate. So imagine you have this is your cost function. You are here. You have identified that this direction, this is the direction in which you should go to decrease your function. But what if you take a very large step in this direction? If you take a very large step in this direction, you would reach somewhere here. And now your function value is actually increased. It's not decreased because your step was so large. Okay. So you want the step to be small. And for that to happen, you want this number to actually make it small. You multiply it with a small constant so that you don't take a very large step and go in the direction of and end up going such a large distance in the gradient direction that your value starts increasing. Is it clear? Okay. Is the log in? Yes, it's natural log. It shouldn't matter, by the way, whether it's natural log or not, because it's just logs are just multiplied with a constant. So for example, if this is my cost function with natural log, if I do the other log, the log to the base 10, it would be just like this. So it shouldn't affect much. But I think it's use just np.log. np.log I think is probably natural log. Any other question? Okay, so good luck. I will, is if x is on the left. Oh, if x is on the left, same thing. So if x is here, the direction of the decrease is this. So you would come here, and then you would come here, then you would come here, then you would come here, and so on. No. If f is on the left, so basically the thing is gradient direction. So let me show gradient directions. So this with green, I'm showing the gradient direction. So the gradient direction here is this. The gradient direction here is this. So these are the gradient direction is this point. Remember, gradient is the direction of the increase, the maximum increase of a function. There is no gradient direction here because gradient is 0. And then gradient direction is here or this because the function is increasing in this direction. So now with red or with blue, I would show, so let me just write it here. So green is gradient direction. Okay. With blue is the negative gradient direction. So negative gradient direction here could be this, this. So you would see that they would always point toward the minima, the direction in which there is a local minima. Is it clear now? The negative gradient direction always points toward the direction in which there is a minimum, a local minimum. Okay, so good luck, give it a try. I'm available in the chat for any questions. At 11:30, we would implement it together and see if there are any other questions. We will try to answer them then. You guys, welcome back. Let me start sharing my screen. Okay. So should we start? Is everyone here? Okay. I need to see a few more yeses in the chat so that you know that we have enough people to start. Okay. Okay. Still, I think we are missing some people. So just very few yeses yet. Let's give it a second. Okay. Okay, so let me write the setup for the question. So the question we have a matrix X, which is a long matrix. Each element of this is a data point. Represent the XY coordinate or X1, X2 coordinate. So we are in 2D space, X1 and X2. And we have two classes. Let's say the first class is somewhere here. The second class is here. I've already stacked all the data points in a matrix, and similarly all the labels in a vector. I think the size is 200 elements, I think. We will look at the data. There are 200 elements here. So the first thing, and I want to write my network as W time X plus B is equal to Z. What should be the size of W? The first question is, what is the size of W? Remember, this is 2 times 200. So what should be the size of W? So this is a matrix product, it's a matrix multiplication. I'm looking at the chart. Size of X is 2 times 200. So what should be the size of W? How many columns should W have? Come on guys, it's easy, it's not that difficult. It's matrix multiplication. The number of columns of first matrix should be equal to the number of rows of the second matrix. So it should have 2 columns. And then since our output is a scalar, Y is a scalar, it should have 1 row. So the size of W is 1 times 2. Okay. Remember, we wrote Z as W0 plus W1x1 plus W2x2. So this is 2-dimensional. W1 and W2, and this B is equal to W0. Does it make sense to everyone? Okay. Okay. So let's assume I was in 4D. Let's assume that I was in 4D, and this was This was 4 times 200. What would be the size of, what should be the size of W? Yes, 1 times 4. Okay. So the number of columns of W are equal to the number of rows of X, and the number of rows of X are equal to the number of output channels, or output, the dimension of the output, in which in this case we have a scalar, so it's just 1. So it's 1 times 2 and 2 times 200. Okay, the rest of the things are fairly straightforward. Sigmoid of Z is defined and the loss function is defined. What else do I need to discuss beforehand? I think we are good. So let's try to go to the code and try to code this up. Okay. Can everyone see my screen?
Yes.
Okay, perfect. So this is the data. We have 2 times 200 times 2 times 200 size matrix for the data and 1 times 200 for the label. So what I want to do is I want to first write this function plot class, which can plot this data for me. Okay, so let's define this function. It can be defined in multiple ways, but the way I do it is something like this. It takes in the data, the label, and a marker. Okay, and I say for I in range, I want to go over each element of the data. So this is Y shape 1. And then I have two conditions. If Y of 1I is equal to 0, then plot the the x1 component of the ith column of the data, and x2 component of the ith part of the data with a red color and a marker. And similarly, if this is equal to 1, then do it with blue and marker. So let's see if it's correct or not. It seems fine. So this basically, it goes to each data point and plots that data point. If the data points belong to class 0, plots it with red. If the data point belong to class 1, plots it with blue. Okay. So let's see. Let's run this. And now let's run this again. Okay. Index is out of bound as it should be. This is 0. Remember, the first row or first column is indexed by 0. And it indeed plots it correctly. I can increase the difference between the two classes by adjusting this number. It takes the two classes away from each other in space. So let's, for the time being, let's keep the two classes very clean, and then we will bring them together and see how it affects logistic regression. Okay. So now let's try to write the helper function. So what do we need? We need a function which would return z for us. So this takes in x, the data, it takes in a w, and it takes in a b. And it returns w times x plus b. So this is the linear part. Everyone's clear on this? Everyone is clear what this is doing? This would do the linear regression part of our logistic regression network. I need some yeses in the chat. If it's not clear, so basically this, our setup was this, right? So input is is x. First we calculate z, where z is wx plus b. Okay. Then we do y hat, which is sigmoid of z, and then we have loss j, which takes in y and y hat. Okay, so the first part is done. We have the z function. Now we can get the z function. By the way, if at any point there are questions, please ask. So it's just a discussion. I won't mind questions. Ask as many as you want. Don't be shy about it. Then let's write a function for sigmoid. So it takes in a z and it returns 1 divided by 1 plus np dot exponents minus z, right? That's how the sigmoid should be. And lastly, we have a loss function. Let's call it return underscore loss. It takes in a y and a y hat, and it returns minus y times np dot log of y hat minus y times np dot log 1 minus y hat. Am I missing something? Is this complete? Remember, we have 200 data points, and loss is a summation over all the data points. This is, how do I do the summation? I need to sum it up. Remember, the data in y and y hat, the data elements are in columns. So I have to sum along all the columns to get a number. Okay, how should I do it? I can just use np.sum, and I can ask it to sum along x's equal to 1, sum along columns. Does it make sense to everyone why I did this sum here in the loss? Okay, okay. Any questions so far? Any confusion about this three helper functions? Again, please, sure. So my y and y hat, y is like this. So I'm y minus y hat is a vector where you have these values, let's say 0.1, 0.3, 0.4. These are the difference between y and y hat for all data points. So you will have this for all data points, and the data points are, total number of data points is 200 in my particular example, 200 data points. Okay, you can see it here. I have 200 data points, 100 for class 0 and 100 for class 1. Now, if you look at the mathematical definition of the loss, the mathematical definition of loss is sum from I equal to 0 to n for all the points, right? J of y I minus, sorry, y hat I. So for each data point, you have to sum the loss. So that's why we have this sum. And the sum is going along the columns because the data points are sitting in the column. Is it clear? Okay, any other questions for anyone? Okay, so it seems like we're good to go. Let's randomly initialize our weight. So I'll just give it np.random.n. And what should be the size of this? What is the size of my weight matrix? In this case, it's a vector, but in general, it's a matrix. What is its size? 1, 2, right? Thank you. Thank you, Nawaf. And what is the size of B? B is just a scalar. I will initialize it to 0. Now I need to, let's do some this. So let's call it losses. Let's initialize it as an empty. You will see what this is for. This is the eta, the learning rate. Let's set it to 0.0001. And I want to do this for, let's say, 1,000 iterations. So what would I do first? we have to do the forward pass. Like I said, we have to take our input through this part first. So let's do it. So Z would be what? Sorry, what do I call it? Return Z, sorry. So Z would be return underscore Z, and it takes in X, W, and B. Okay. Then I have to go get Y hat, and Y hat is the sigmoid of Z, and then I have to get loss, and loss is return underscore loss of Y and Y hat. So the forward pass is done. Okay. I want to store these values of losses because I would do plotting. So I will just append it to my list. LS is the list of all the losses. Okay. Now we need to do the calculating the gradients. Okay. So I'm going to need your help. So what was the dj by d z? What was this? We calculated it. This was y hat minus y. Okay, you can refer back to the notes, but this is what it is. In fact, let me write all of these. So dj by dy hat was, I think, y hat times, let me just look at my notes. Okay, so this was y hat minus y divided by y hat times 1 minus y hat, and dy hat divided by dz was y hat 1 minus y hat. Okay, so dj by dz would be dj by dy hat times dy hat divided by dz, and you can see that the product of these two is this. Okay, is everyone with me? Everyone understands how I calculate the derivative of j with respect to z? Okay, perfect. So let's just code it. Let's call this dz. So dv represents the derivative of z or j with respect to z, and this is y hat minus y. Then the derivative of j with respect to w, the derivative of j with respect to w would be derivative of j with respect to z times the derivative of z with respect to w, and the derivative of z with respect to w is this is a matrix. This is X transpose. I will explain where I get this from. I'll go back to the notes and calculate it for you. So I will just put in the values. So this is dz times at matrix product x dot t, and similarly db is np dot sum dz, and x is equal to 1. I'll explain these two. We have done it for scalars, but we haven't done it for matrix. I'll go back to the notes and explain it. It's the same form. So for scalar, it's dz times t, just the particular component. But since we have matrices, this becomes a matrix product of x transpose. And this becomes a matrix product with a unit vector, but a matrix product with a unit vector is a dot product, which is a dot product of a vector with a unit vector, which is its sum. So I'll explain both of these in the notes in a bit. After that, once we have this, we just have to update our weights. So weight would be plus equal to negative equal to learning rate times dw, and b would be negative equal to learning rate times db. And I think that should do it. Let me just double check everything. So I calculated the gradients and I updated the value of my parameters. Seems fine. Let's just run it and see if there are any. Okay. There is spelling problem here. Okay, it seems to work fine. Let's just plot the loss. Okay, so the loss is decreasing, which is a good sign. It means that it's learning something. Let me just go back for a second to the notes and explain how I get these expressions, these two expressions, and then we can come back and do some additional things there. Okay, so we have z is equal to wx plus b. If we, of course, we can stack all the data together and make a big vector x, where x is a big matrix x, where x has the first data point x0, second data point up till xn data points, right? And then this becomes a matrix or a vector depending on the type of output that you have, wx plus b. And this is a matrix now. So if you take the derivative of z with respect to the matrix W, this is equal to X transpose. And if you take the derivative of C with respect to B, this is just a vector of ones. This is 1, 1, 1. Sorry. So in order to make this sum possible, there is, of course, a big one vector, right? Because this is a scalar. In order to make its size similar to this, when I say B, it's, of course, we use broadcasting, so everything is clear. But this has a big vector of ones. Why does it have this? Because the size of this and the size of this has to be same for them to be added. Okay? So this gives a big vectors one, a big vectors of one. And again, I think this is also transpose. And when you multiply them together, so when you take the product of this, so when you're finding the loss function of the derivative of loss function with respect to b, this is dj dz times dz times db. And this, of course, is a big row vector. And then this is a big vector of ones. If you take their matrix product, this is sum. This just becomes a sum of element-wise product. That's why we have a sum there in our code. And this is just a matrix product with an X transpose. Okay. Is everyone clear with the identities, the matrix identities? How do we get this? Okay, perfect. Let me go back to the code. Okay, so let's do a couple of things. Let's see, the loss is very low. Let's calculate the value of y hat through our network. We have it here, it's calculated. So let's see how y looks and how y hat looks. So, plt dot plot y. Hat. Let's see both of these. Okay, issue. I have to make them column vectors. Okay, so can somebody tell me, is it good or is it bad? So let me just give them color. So y is in blue and y hat is in red. So what do you think? Is it a good model? Is it a bad model? So the blue are the original labels. These are y, and the red are y hat. What does y hat represent in a logistic regression model? Y hat represents the probability of the class label being 1 given the data point. So what is the belief that your network has in that particular point belonging to class 1? So what can we see from this figure? So we see that for all data points which were 1, our network has high confidence that the output label is 1. So it has actually learned it, that if the true label is 1, then probably this belongs to class 1. And for zeros, uh, it has high probability that the label belongs to class 0 because the probability of it belonging to class 1 is low. Does it make sense to everyone? One thing which I didn't explicitly mention in the lecture notes so far. So probability of y equal to 1 given x plus probability of y equal to 0 given x is equal to 1. So if one of them is low, if one of the probability is low, the other one would be high. If the probability of it belonging to class 1 is low, it means the probability of it belonging to class 0 is high. Okay, let's do another thing. Let's call it plot scatter and y in hat. This is a scatter plot. And this is how it looks. If it were perfect, if let's say we had absolutely perfect learning, how would this scatter plot look? How would you expect it to be? Two dots, exactly. You would have a dot here where it means that for y equal to 0, y hat is also equal to 0. And for y equal to 1, y hat is also equal to 1, if it was perfect. But of course, it's not perfect. It's still good enough. We would not have any misclassification because what we do is typically for classification problem, after we get y hat, we just simply threshold it at 0.5. We say that anything greater than 0.5 means class 1, anything less than 0.5 means class 0. So that's how we have our output label and our real label are exactly the same. Everyone is clear about what we have done so far? Are there any questions? Okay, perfect. Let's try to do the same in scikit-learn, because you might not want to code your problem every time, so you can just use sklearn dot models. Just import it from there. You can import the logistic regression model. After you have imported it, you can instantiate an object from this class. And then you can just fit this with your data. So this is X and Y. You can get these type of problems because it might be expecting the matrix to be a row vector and you might be giving it a column vector. So just transpose and try and transposing it would work. And then you just do this. You say that, okay, y new is model dot predict for x dot t. Then we can do something like okay, so this is very good. You can see that logistic regression model for scikit-learn is very good. It gives you perfect answers, which means that probably we can improve our results as well, maybe by increasing the learning rate a bit. Let's see if we can improve it a bit. Oh, they might have thresholded it. It might be the output from a threshold. So that's why you get it perfectly. Okay, let's make the problem a bit difficult. So if we make the problem a bit difficult, we bring the data a bit close to each other. Let's say 1. So now there would be some overlap of the two data classes. This is a relatively tough problem. Let's do our model. And let's look at the loss. I think I haven't run this code. Okay. Okay, so you can see now the loss is quite high. It's 100. But let's see. Okay, so I need this here. The dot would do better. So now you can see that these points, these are incorrectly classified. And the reason is, why can't we, for this data, why can't we get it 100% correct from simple regression model, which takes in the X and Y bases only, X1 and X2 bases only? Why can't we get 100% correct results? The thing is because you have a linear model. So your classifier is actually a line and anything above it is class 1 and anything below it is class 2. And there is no line which can perfectly classify this data, right? So that's why your error is never going to be 0. You're going to have some errors like this. And you can similarly see it from plot.scatter. Okay, let's give the same data to logistic regression from scikit-learn and see if it can do a little better, but I don't think it will be able to do much better as well. So you can see that it labels some points correctly and then it labels some points incorrectly. So this you can actually, you would need a confusion matrix to see it exactly. So this is basically the summary of logistic regression. One thing which we can do is we can try to plot the decision boundary and see how it evolves with time. Would it be of interest to you guys? Should we like plot this data along with the decision boundary as we learn? Do you want to see it? Okay, so let's do it. Let me copy, let me make the problem a little easy, maybe give it 3. Okay, and let's copy this code. Let's come here. Okay, so let's do something. Let's come here and let's plot the decision boundary. So what is our function? Our function is W1. I'm removing sigmoids, but it's there. Sigmoids is there. Again, sigmoid doesn't mean anything. We just want to find the linear function on which it's equal to 0. Sigmoid would just make it greater than 0.5 on one side and less than 0.5 on the other side. W1 x1 plus W2 x2 plus b equal to 0. This is the decision boundary. This is the line on one side of which is probability greater than 0.5, on another side is probability less than 0.5. How do I know it? Because sigmoid of 0 is 0.5. We plotted it, right? Is everyone with me? Does everyone understand why I'm interested in this as a decision boundary? Because this is the line above which you would have probability greater than 0.5 and below which you would have probability less than 0.5. Okay, so let's try to write it as a line in space. So if I do it, x2 would be minus w1 times x1 minus b divided by w2. We have to plot this, right? And this would give us the decision boundary. So let's copy this line of code. And for each iteration, let's plot in a figure. Let's create a new figure. Let's do this. And okay, which is the range for my data? My data is x is from -5 to 5. So I can call it xc for x clean, np dot in space. So let's say from -5 to 5, maybe 10 points. It doesn't matter if I give it 1,000 or 10 because it's a line root connected, so it's fine. And then I do this. I say yc, which is the y component, would be minus w0 times xc minus b divided by w1. I think that should do it. Just to be sure, I will do this. And then here I do plot xc and yc. I don't probably want to do it each iteration, so I will do it I mod 10 is equal to 0. So every 10th iteration, and I think that's probably a little too much. Let's give it 100. Let's not give it too many iterations. So I will have 10 figures, and let's see. Let's see what do we have here. Okay. Let's see what's the error. W is not defined. This is not defined. This is W. Okay, so I probably don't need it from -5 to 5. Let's make it -2 to 2. And probably this would be nice if we have it in the title. I'm going to do something. Just bear with me for a second. Is Okay, so let's see. So to start with, this was our decision boundary at iteration 0. It's quite bad. You can see that these points are misclassified. After 10 iteration, it becomes this. After 20 iteration, it becomes this. After 30 iteration, it becomes this. 40 iteration, 50 iteration. You can see it's improving. 60, 70, 80, maybe let me do this. Probably let's plot it every 50th iteration, and let's do it for 1,000. That's going to be some 20 figures. And you can see that eventually it does learn to separate the data almost perfectly. Some points cannot be perfectly separated, but it does a very good job. Probably we can make the figure a little better by doing this. -225. Oh, that's much better. So let's look at it from here. So to start with, the decision boundary is this, and then it's slowly start improving. You can see that it's capturing the data perfectly, almost perfectly, and that's how it looks. Any other questions, any suggestions, any other thing that you want to see or do before I leave you guys to try this exercise for yourself? Feel free to ask anything, any other insight that you want to do, or let's say you want to make the data complex. I don't know, whatever you think would be helpful for your understanding, you can ask and we can do it. Okay, so are there any questions? So in real situation, you always use sklearn, and not necessarily. You can use sklearn. I'm not using sklearn here, but of course, sklearn gives you a lot of flexibility. So you should use sklearn if you have the opportunity rather than coding it yourself. The whole idea of coding it is so that you understand that there isn't any magic under the hood. It's very simple algorithms, simple calculus and linear algebra. So if you want to just use the tool, yes, I would recommend use sklearn. If you want to use it, let's say you need to modify it for a particular application, you want to, let's say, rework the equations, add something else, remove something, then you probably would have to code it yourself. Any other questions? Okay, so give this exercise a try by yourself now. I will be available in the chat till 1. I won't explain anything new. This basically caps the first week and the first half of the course. And the second half, we would be focusing on some optimization review. We would look into detail, like where did these gradient descent method comes from, what is the motivation for them, what do we have to be careful when we are using methods like this, and then we would do neural networks and convolution neural networks, all the theoretical part of them, and actual implementation in packages like PyTorch, maybe even TensorFlow. Okay. I'm thinking that I'm going to give you guys, ask you guys to like do a small project, small individual project toward the last 2 days. Like every day we do some exercises. So the last 2 days I would just create a small assignment. I'll ask you guys to select some data and do the small assignment in from 11 till 1 for the last 2 days. So you have like around 4 hours to do that. You can, of course, ask questions and I can help you with that. But that would be a good practice for you guys to implement what you have learned. So I will finalize the detail of that over the weekend. It would be on the course website instruction page. And you can go there and see what the requirements are and how you're going to supposed to do it. Okay. Any questions? Okay, so I'm going to stop sharing my screen. I'll be available in the chat. Good luck with the exercise. Thank you. Okay, guys, can I have your attention for a few seconds? So I've uploaded the lectures on the website, the slides, I mean. The video would be uploaded at the end of this at the end of this class. It'll take around an hour or two, and then you will find the video as well. So I'm available for the next 10 minutes, but if there aren't any questions, I would just close the video. I'm looking at the chat. If there are any questions, please ask them there. Thank you.